Hello, thank you for tuning into my talk. I hope everyone is well. My name is Stephen Mills, and I am a research statistician developer with the SAS Institute. Today, I wanted to talk to you a little bit about neural network-based strategies in SAS Viya for forecasting with time series. So, machine learning models, like neural networks, have often been dismissed as potential models in forecasting. There's a couple of reasons for this. One is that they're not very good at learning autoregressive features common in time series like seasonality or trend. And the second is that they require quite a bit more data than classical models. However, the M4 forecasting competition results were dominated by ensembles of machine learning and statistical methods. In fact, the first and second place contestants included machine learning techniques, and nearly 3/4 of the best results were ensembles of different models. An ensemble of models often generalizes better to new data than a single model because different models are better at identifying different features in the data. And additionally, noise or error in any of the models is less impactful when it's averaged with other forecasts. From this point of view, it makes sense to use diverse models when we're creating ensembles. Neural networks can make valuable contributions to these ensembles because they're very good at modeling nonlinear behavior, and they're also very good at identifying complex interactions between variables. With that in mind, I'd like to talk about the neural network modeling strategies that are designed for panels of time series in SAS Visual Forecasting. We've designed 3 modeling strategies that include neural networks. They are the panel series neural network, the stacked model, and the multistage model. To show you how to use each of the modeling strategies effectively, I'm first going to explain how the data is pre-processed differently from classical time series applications. This is to overcome some of the shortcomings of traditional neural networks. Then I'll give you a brief overview of each of the 3 modeling strategies available in visual forecasting. Next, I'll show you a case study comparing the neural network-based and the classical forecasting methods. And finally, I'll cover a few tips and common problems that you might encounter. One big difference between machine learning and time series models is that machine learning algorithms typically don't care about the order of observations and will partition the data randomly. Since time series are ordered data, and the more recent observations have more predictive power, ordered sampling makes more sense instead. So when we are partitioning the data for forecasting with neural networks, we put the oldest data in the training partition, shown in the yellow, and then we use newer data for the holdout and the absolutely newest data for testing. Neural networks also require significantly more data than a typical time series model. With time series processing, if we are modeling a panel of series, each phi group is diagnosed and has its own model fit to the data. However, a single time series typically doesn't contain enough data to train a neural network. To increase the amount of data available for training, each phi group is concatenated together to form a single long time series that's fit to a single neural network model. So in the slide here, you can see yellow, blue, kind of brownish, green, and purple blocks, each representing a different time series. So we'll have repeating timestamps that start over at the beginning of each color. The individual series are delineated within the neural network algorithm by using bivariables as categorical inputs. This lets the neural network do things like determine if one particular series has a lower average level, or perhaps some features are less prevalent in a particular series. Feature extraction is another technique that we use to increase the amount of data and also to help overcome some of the shortcomings of neural networks. So neural networks, I mentioned, are very bad at detecting autocorrelated features like seasonality or trends. But if we create lagged versions of the variables in our input data, then we can allow the neural network to use past data when it's trying to evaluate each observation. In the table below, you can see that I've created lagged versions of the dependent variable y in the first row of yellow columns, or the first two yellow columns, and lagged variables of the x variable in the second group of yellow. Additionally, a trend or an exponential smoothing model can be fit to the dependent variable and included as an input. This helps the neural network learn level shifts, trends over the course of the series, and adjust for those. Finally, seasonal dummy variables can also be generated. These can be generated at any interval that you like, any standard SAS interval, and they don't have to conform to the interval of your data. So if you had weekly forecasting data, you could generate quarterly seasonal dummy variables in order to keep your, or in order not to have redundant information. There are three strategies in visual forecasting that use neural networks and these pre-processing techniques, as I mentioned earlier. The panel series neural network is the first. The block diagram at the bottom of the slide shows the typical workflow through the neural network modeling strategy. First, any transformations and data standardization is done, and then the feature extraction process that I described previously is performed. Next, the neural network fits a model to the data using a training and validation cycle before it finally reverses any transforms and standardization to generate the final output. The second strategy is the stacked model. This is a hybrid of a neural network and time series models. First, a panel series neural network is fit to the data. Then the error or the residuals left over are modeled with time series. And finally, the two forecasts are added together to generate the final forecast. This takes advantage of the advantages of machine learning and time series techniques. And finally, the multistage model is a bit of a twist on hierarchical forecasting. The lower levels in a hierarchy, where your data may be much more noisy and nonlinear, can be modeled with neural network or regression models, while the upper levels can be modeled with time series. Finally, the forecast will be reconciled to the user-specified level to generate the final output. To illustrate the forecasting power of these modeling strategies, I'm going to show some results from a case study now from the Array of Things project in Chicago. The Array of Things project is a bunch of sensor nodes distributed around the city that include environmental sensors like gas sensors and light sensors, temperature, humidity, microphones. They continuously collect data, and I've downloaded from their website the data from October 2018, and I've accumulated it to an hourly time series. There was a lot of bad data in there. Of course, raw data is often dirty and needs a lot of cleaning. But after cleaning and selecting variables, I was left with 27 series of 720 observations each. The dependent variable that I'm going to be forecasting is the ozone sensor output. And to predict that, I'm going to use 5 independent variables: temperature, humidity, and 3 light sensors, one for ultraviolet light, one for infrared, and one for visible. Ozone exposure is an interesting thing to look at here because it's closely linked with respiratory problems like asthma. In fact, the risk of having an asthma attack after you've been exposed to high levels of ozone remains high for hours. So it's an important thing to be able to monitor and know what you've been exposed to throughout the day. In addition, with COVID-19 in the world now, this could further complicate respiratory symptoms for those patients. The data only has two hierarchy levels, so I'm going to use the panel series neural network and the stacked models. If it had more levels in the hierarchy, or if the lower level was more noisy, then a multi-stage strategy would be a good candidate. The extracted features that I've included are 3 lags of all the variables, seasonal dummy variables for the hour of the day, and a damped trend model for the dependent variable. So here are the results from some of the forecasting. The plot on the left compares the output from the panel series neural network with hierarchical forecasting. The shaded area, the gray shaded area on the right is the forecast horizon, so that's future predicted data. And to the left in the white area is historical data. So we can see the historical fit and then the fit in the forecast region. The tables on the right shows the weighted MAPE measurements, measuring the error in the model fit. In the top table, you can see the stacked model significantly outperformed hierarchical forecasting with in-sample data. And I should mention hierarchical forecasting is really just kind of the auto forecasting version of this because there aren't very many hierarchy levels. I was not able to calculate out-of-sample weighted MAPE for the stacked model because it doesn't yet support incremental forecasting. However, the panel series neural network does. So I was able to easily calculate the out-of-sample weighted MAPE in that case. And here we can see that both the in-sample and the out-of-sample MAPE for the panel series neural network are lower than that of the hierarchical forecasting, indicating that we have achieved greater accuracy with the neural network model. Now you can calculate the out-of-sample MAPE for a stacked model type of problem in the coding environment, but it's not supported in the UI yet. So, cool. We have good results, but these results are only good if we can use them. And I know training neural networks can take a long time. So how long does it take as we scale up the data? If you recall, the original table that I had was about 20,000 observations. And here I've scaled the data up to 2 million observations. And we can see that the training time on the left increases linearly as the volume of data increases. So that's a good sign that our training time isn't blowing up. So that's great news, but what about if our series are short or our data is small? We know that neural networks need a lot of data to train a good model, but how much is a lot? So I did another experiment with this study where I shortened the time series. So starting on the right at 720 observations and decreasing the number of observations in each series, we start to see an increase in the error right around 350 or 400 observations. So this gives us an effective estimate of the lower bound of how long our series need to be to use the neural network models. Now, reducing the number of bigroups in a series doesn't affect the error the same way. It's not really deterministic, and it depends on the similarity between all the different bigroups in your panel data. This should give you a pretty good foundation to start experimenting with the neural network modeling strategies. So I'm going to give you a couple of tips and common problems to look for while you're doing so, and those should help you out as well. One of the things that you should keep in mind is the effect of missing values, in particular in combination with generating lagged versions of variables. In the table here, you can see that the first observation for lag 1 of y is missing because there was no historical data to create that time-shifted value from. This propagates further down in time on the second lag and the third lag. Notice there's also a missing value in the third observation for the x variable. As we create lags of this variable, the missing values also propagate forward through time and cause more of our total number of observations to have missing values. The problem with this is that any observation with a missing value is going to be excluded from the neural network training. If you're not careful and if you have many missing values, then you can quickly reduce the amount of data that you have, and you may not have enough data to train a good model. Let's see. Another important thing to understand is how the training time is affected by the selections that you make in modeling. For example, using the data from the array of things case study, I had one time ID variable, one by variable, one dependent variable, and 5 independent variables. After creating 3 dependent variable lags, 3 lags each for all of the independent variables, adding a trend and seasonal dummy variables for each hour in the day, I now have 51 effective input variables, which causes a large increase in complexity and the training time required to fit a good model. This is further compounded by the structure of the neural network. So here on the left, I have a diagram, a simple example of a very small neural network. One input layer, one hidden layer, and one output layer. And on the right, I've shown an enlarged view of the central, or the center node there to illustrate the math that is calculated for each node. So the input layer is going to have one node for every effective input variable. So this has already increased to 51 based on my case study data. And now every one of those nodes is going to be connected to every single node in the hidden layer, the very next layer. Each connection has a connection weight parameter, W sub I. In addition, the different nodes, aside from the input nodes, have a bias parameter B. So you can see how quickly these parameters multiply and can get out of hand. The increase in training time can be exponential with the number of nodes in your hidden layers and the number of variables that you are, or the number of features that you're generating. So I think that should give you a pretty good amount of information. I encourage you to read my paper for more details and more tips for using these strategies. So I've shown you how these forecasting strategies were designed for use, how these neural network strategies were designed for use with time series. I've shown how they can improve the forecast accuracy for certain data characteristics. And finally, I'd like to leave this point with you. Parsimonious models generally converge faster and generalize better. There is often a tendency to make a large neural network and lots of inputs and lots of nodes. But multi-collinearity will damage your forecast results, and keeping your model simpler is usually the best bet. If you have any further questions, I encourage you to reach out to me, and I look forward to hearing from you. Thanks.